All right, good day, everyone, and welcome to this Gradle webinar. I'm your host, Oliver White, and joining us today for Gradle Artifact Transforms and Deeper Build Insights are two of my favorite engineers at Gradle, Nelson and Inaki. Today, we're talking about artifact transforms with Gradle. And if you've never heard of it, that's not strange. It's a powerful but often overlooked aspect of Gradle Build Tool that can open the path to deeper build insights, and that's the reason we're talking about it today. So while we wait for folks to get settled with their drinks and popcorn, just a couple of housekeeping items to go over. If you're looking to learn more about developer productivity with Gradle, Maven, Develocity, and DPE, we invite you to visit DPE University, which offers free self-paced courses with certifications for completion. We currently have 10 courses and plan on releasing a few more in the coming months. Finally, this Gradle webinar, our DPE City Tours and DPE Summit this September 24th and 25th. Early bird tickets are ending this Sunday, so if you haven't got it yet, now's a good time. This is all made possible by our hundreds of happy Develocity customers, including Netflix, who saves nearly 300,000 developer hours per year on builds and tests using Develocity. You can find out more about that on our website, gradle.com. All right, that's it from me. Let's hand it over to Nelson and Inaki. Gentlemen, thanks for joining us today.
Thanks, Oliver, for the wonderful intro. And yeah, I'm going to jump right into it. So before we start talking about what artifact transforms themselves are, we need to back up a second and start with a bit of terminology about Gradle. So let's start talking about variant attributes in the Gradle Build Tool. So variant attributes give semantics and variants to Gradle to find the best matching variant of a dependency. So every dependency has attributes, more one. There are default attributes and also custom attributes that you can add to dependencies. An example would be org.gradle.jvm version, which expresses the JVM version used to create that artifact or the compatibility of that dependency. Another one is org.gradle.native.architecture, which can be something like x86 or ARM64. Another example would be org.gradle.library elements, which can be something like jar or classes. So that represents the type of that the dependency is in. So let's dive into a really, really simple transform example to explain what this works. So let's say you have a org.gradle.library elements equals jar, but you want that dependency in the form of org.gradle.library elements equals classes. The unzip transform can take the jar and transform it into classes by doing a unzip on that. So it's very straightforward, right? That's at the very basic, that is everything you need to know about what artifact transforms are. Yeah, so there's many different ways to use them, and there's a little bit more information that I'll explain. So an artifact transform is a unit of work in the Gradle Build Tool, just like tasks are also a unit of work. Artifact transforms can only have a single input, which is an artifact, and a single output, although with a caveat that single output can be a directory, which can have multiple things inside of it. Artifact transforms can be cacheable, and they can be up to date. They also fit into Gradle's dependency management engine, as I explained before, with the attributes, and they basically modify a dependency that already exists before it is used by modifying the dependency attributes, as I explained. And the benefit of artifact transforms is that multiple different tasks in your build can reuse already transformed artifacts. So let's say 3 or 4 tasks depend on the class's version of a dependency. Each one of those tasks doesn't need to unzip that task 5 times. They can just reuse the output of a previously transformed artifact. And you can imagine as your build gets bigger and bigger, this saves a lot of time. So yeah, this webinar is a little bit Android specific, but artifact transforms are used actually in all sorts of builds. But we're going to dive into a couple of Android examples here. So the Jetifier transform, that is a transform that transforms a dependency from the old Android libraries to the new Jetified version of that dependency by modifying the class path of it. There's the dexing transform in Android, which modifies an output into a dex file, which is used at the runtime. Instead of the normal Android runtime, the normal Java runtime. Android uses the Android runtime, which runs on DEX files instead of Java class files. There's the extract AAR transform. So for the audience who's not in the Android world, an AAR is very similar to a jar file. So the extract AAR transform is actually the exact same thing as the unzip transform, but for Android. And then one more, the build API class path entry snapshot transform. You might see that later on. I know it's a mouthful, but all it is it takes a dependency and it creates an API class path snapshot. So instead of having the entire dependency, it just has a snapshot of the API surface, and that can be used for compile avoidance. Okay, so a couple other things. So build authors don't directly request an artifact transform to be executed. They just ask for dependency with certain attributes. And then Gradle automatically schedules transforms between units of work. And transforms can depend on tasks, or they can depend on transforms, and there can be multiple transforms in what's called a transform chain. A little bit of terminology while we're here, since that we're going to go into that later on. So the transform action is the code to implement a transform. So in this case, it would be the extract zip class or the DEX transform class. A transform step processes the result of previous transforms. So that is a step in a chain, so to say. And a transform chain is a series of transformations. And then a transform execution is the actual act of running the transform action, which can also be avoided if the transform is coming from the cache or it's up to date. And then one more thing, project level transform registrations bind the transform action to a set of inputs and outputs. Okay, so hopefully all that terminology, you've memorized it all. You know exactly what I'm talking about going forward. No, I know it's a lot, but it'll make a lot of sense as we dive into this a bit further. I also wanted to mention that artifact transforms are now visible in Build Scan. So this has been out for a bit of time now, but in case you haven't updated to the latest version of Develocity, as well as the Develocity Gradle plugin and the Build Tool version, you need all these moving parts together to be able to see these insights. And when you have transforms in your build scans, this is just a little bit of what it looks like. In your build scan, you'll see 3 transforms, for example, at the top next to the tasks that executed. You'll also see the attributes that were changed. And then you can also click on a transform. You can see the source and target of the transformation in the details page. And you can see how much time that transform took. You can also see predecessors, that is what dependencies that transform had. In this case, you can see this transform had both tasks and other transforms as dependencies. This also fills up space in the timeline that used to be empty. And you can also see transform failures in your build scan. And with that little intro, I'm going to hand it over to Inaki for the next set in this presentation.
Thanks, Nelson. In this section, we'll do a quick overview about how to create artifact transforms. Similar to task types, an artifact transform consists of an action and some parameters. The major difference to custom tasks is that the action and the parameters are implemented in 2 separate classes. The implementation of an artifact transform is a class implementing transform action. You need to implement the transform method on the action, which converts an input artifact into 0, 1, or multiple output artifacts. Note how the implementation use the annotation input artifact to inject the artifact transform into the action. The implementation of the artifact transform needs to register its output artifact by calling transform outputs dir or files. The parameters are implemented on a separate class, and in this example, we are declaring an input parameter that later is used by the injected property parameters. The input artifact is used to inject the artifact transform into the action. If we want to make the transformation type cacheable, we could need to use a normalization annotation such path sensitivity. Remember that the input artifact is a dependency, which may have its own dependencies. If your artifact transform needs access to those transitive dependencies, it can declare a file collection and annotate it with input artifact dependencies. when your transform runs, Gradle will inject the transitive dependencies into that file collection. Artifact transforms, as Nelson mentioned, can be cacheable. We can map with annotations, cacheable transform, or on the other hand, we can disable the cacheability by specifying the annotation disable caching by default. In order to register an artifact transform, you must use the register transform within the dependencies block. There are a few points to consider. The from and to attributes are required, from which input artifact attribute is coming jar to the new attribute. And then you must register a transform on the project that has the configuration that will be resolved. Finally, we need to create or define the task that requires the transform artifacts. In this case, we are declaring the artifacts of the runtime configuration. We are defining that the runtime configuration will consume artifacts with the new attribute, with the attribute new attribute. Now that we have covered the theory and how to implement artifact transforms, this might seem like an advanced topic in terms of dependency management, and you may be wondering how this relates to the Android builds. In this section, we will see how transforms are widely used in our builds. For this example, we are going to pick the project now in Android. This project is an open source Android application created by Google, and it serves as reference to demonstrate best practices and modern Android development techniques. In this project, we are going to execute the task assemble debug, and what we have is a build that is executing more than 5,000 artifact transforms. So they're quite present there. Those transforms are coming from different plugins like the Android Gradle plugin, or Kotlin Gradle plugin, and Hill. I would say that the Android Gradle plugin, AGP, is the Gradle component with the most widespread usage in terms of artifact transforms of the ecosystem. I think that they are providing more than 20 different artifact transforms, and I think that I wouldn't be the right person to talk about internals of the transforms in the Android Gradle plugin, and also it took more than 1 or 2 hours, but instead we are going to do an inverse exercise. Given the information that the build scans are providing in terms of artifact transform, for the same build, we are going to focus in one particular dependency, and we will analyze its path in terms of artifact transforms. So I'm taking one. It's not important, the dependency in this case, but it's company's Gradle Painter. And we can see that there was like 20 different transforms during the build execution. Let's see how it started. Everything starts, right? So with the first request of this dependency, that is an AAR, as Nelson mentioned before, AAR, jar. So that's implementation details here. But analyzing the transform execution on the build scan, we can get what is the first execution, the first transform executed. And the first one is extract AAR transform. That's requesting, well, the input artifact with an attribute from AAR to an Android explode A. Perfect. The same input artifact that has been transformed, this chain, can execute different transforms into different output artifacts, as we are seeing here. For the same Android explode AAR, we have an Android AAR transform generating different outputs: Android res, Android assets, Android manifest. This is just a subset of the different transforms with AAR transform, because in reality, we have 8. Okay, the initial input, the AAR, or the dependency with the attribute AAR, can execute another transforms in parallel as well, right? Like here, where we are seeing that AAR to class transforms, converting AAR to an Android classes. And from the Android classes jar output, we observe that there is a transform executed with the type dexing with class path transform. This transform will generate an output with the type Android dex. And Android dex, as Nelson mentioned before as well, right? That's something that we are more familiar in the Android world, right? So it's closer to our knowledge in terms of the Android build. But the reality is, as I mentioned, with 20 transforms is complex. So this could be like just a subset of what's going on with one single dependency across the build in terms of artifact transform dependencies. Now let's pick one specific transform, the AAR transform that goes from Android explode AAR to Android manifest. At the build scan, if we go to performance transform execution, we have a list of the different transforms executed, and we have a small window with the details of the transform. Additionally, there is a tab with the request that represents that which task requests the artifact transform. So given this information, we have the process demo debug manifest. We can extract the type, and in this case, it's a process application manifest. So if we repeat the process for all the transforms displayed on the diagram, we have a better understanding of when and where those transforms were requested. Again, the one of the best examples is the DEX merging task. This class that it's going to merge the different DEX files of external, internal, or in the project dependencies. So it's the one that actually is requesting a dependency that requires a specific input within a specific attribute. That's the action that triggers the transform. Okay, perfect. Okay, Kotlin Gradle plugin. The Kotlin Gradle plugin is as well using artifact transforms. If we explore the same screen as mentioned before, performance, transform execution, we can see tons of different transforms related with classpath snapshot transform. If we are using Kotlin 2, this transform, the type is a build tools API classpath entry snapshot transform. And I'm not going to enter in too many details, but as Nelson explained, the incremental compilation of that JetBrains is providing is going to store the application binary interface of the compilation class path of the Kotlin invocation, of the Kotlin compiler invocation. So with that, we are going to still enjoying the incremental compilation when one dependency is updated, and we're going to need to compile the entire compilation unit. So what's interesting for us in this talk here is that in the code of the Kotlin Gradle plugin, we can see how when we are enabling this property, that is default, by the way, since 1.8 or 1.7, the artifacts of the configuration, of the class path configuration for the Kotlin compiler are going to set that the dependency, the input artifact, has to contain the attribute class path entry to snapshot. And then in the dependencies block of the Kotlin Gradle plugin, they are registered in the transform saying that the from is going to be a jar and to is going to be the class path entry snapshot artifact type. And that's why we are triggering the action, and we have the different transforms that happens at the beginning of the build, and those transforms happens for each Kotlin compiler invocation. Of course, as Nelson mentioned, if the transform has been executed, it's going to be reused. So finally adding transform information in the build scan, we have seen the theory, we have seen some practice, we have seen that it's used in different plugins, but what means as build engineer, right? So we have this information, because at the end, looks like that this just a matter of dependencies, right? But in our opinion, right, so adding this transform information on the build scans open new possibilities to find potential optimization in our builds. And we are going to give you just a use case that we found in our internal investigations. That's what we call the case of the material icons dependency. Okay, so everything starts with the same project or the same build that we are getting familiar with now in Android. And one of the common practices, right? So in order to understand what's going on in this build, a little bit more context, this build was executed in CI, GitHub Action Runner for CPUs, 6 gigs of memory. Well, we want to understand why is slow. So the first thing is, we are going to order the task execution by duration, and we are seeing that the merge x demo debug is taking 3 minutes. So from there, we started our investigation, and on the build scan, we can open the small window right to close to the task name on the timeline. And what we notice is that in terms of fingerprinting this specific task, on the type, that's text merging task, is 1 second. The task action was 15 seconds. The build cast 5 seconds. But the artifact transform execution, it was 3 minutes. So something that was not was wrong, right? So thanks that we have this information on the build scans, we continue the investigation. Following the same approach on the performance transform execution, we can order by duration, and this gives us a list ordered by the duration of the different transforms. And what we have is that the material icons of the dexing with class path transform was taking 2 minutes and 1 minute, with the ones that we were considering, I don't know, slower. As I mentioned before, if we click on the details of the transform, we can get what's the request, which task requested this transform. And guess what? It's the slower task in the build. So the slower task in the build is requesting the slower transform in the build. So let's see more in detail what's going on with this transform. In the details of the performance transform execution transform, we can see, similar to the task, a complete information about the transform, like the fingerprinting, build cache, and action execution. What caught our attention here is that the action execution, it was 2 minutes. So there is no problem with the build cache, no problem with the fingerprinted inputs and the build cache anyway. So I see like 7 megs per transform. Maybe it could be something, but still, all the time was with the action execution. And well, so maybe we can start diving in the Gradle plugin code and check the implementation of the dexing with class path transform, right? So, but we got a different approach. So instead of going to the low level in terms of getting the Gradle plugin, we wanted to analyze what's the impact of the same dependency in other transform types. For instance, for the type ASM classes transform, we noticed that the same dependency represented 41% of the aggregated duration for the same transform type. So it's only 16 seconds, right? So, but still, represent 41%. Something is going on. And finally, what confirmed as well with the Giacoco transform that the same dependency, only 11 seconds, but still represented 31% of the aggregated duration for the same type. So definitely, this dependency had something that is affecting the duration of the different transforms. And well, we are happy to have like these results because we don't have to dive in the code of the dexing with class path transform. So we analyzed a library. Well, we downloaded the library and we realized that, well, so it's like 35 megs, 11,000 classes. And we thought, well, maybe we can do a quick experiment and see how it's affecting this dependency to the build. We removed the dependency it was providing with Nike in the project now in Android, and we provided manually the required classes used by the project now in Android. So it was like a dance of icons, different implementations, and so on. So when we compare the builds, what we have is that removing the library and providing manually the classes required was decreasing the duration of the task by 46%. And it was reducing the transform duration of the same task 50%. So still, the artifact transform execution for the same task is 1 minute 35. That's something, well, considerable, but it's not like the 3 minutes, right? So just by doing this, they change. So looks great, but again, so this is just for a specific task. And what about the overall build time? Because again, so we noticed that the impact on this dependency, it was not only about the dexing with class path transform. There are another types affected by, not affected, but they have considerable time, right? So for this specific dependency. So we measure the main task, the same task, assemble debug, 100 iterations on a fresh agent. So that means that we are not using caching, right? So for any aspect. And the results gave us a 15% decrease on the build time and 22% decrease in execution time. And the only change applied was to provide manually the dependency of the classes required in the code that comes from the dependency material icons. You have the results of the experiment as well here. And just, well, of course, this was like just an experimentation on the transforms and analyzing the data thanks to the build scans, right? So on a fresh agent. But it was quite interesting to see how a single dependency could affect at least this 15% of time in overall build time. So, and with that, thank you. I'm going to go to Nelson again.
Thanks, Inaki, for the wonderful insights and all the different things you can find in build scans with artifact transform insights. I'm also going to add a little bit to that of something you can find in your build scan with artifact transform insights. So if let's say we're looking at this build scan, and here we see for the Dex merging task, our favorite task, we were just looking at it, we see that it spends 1 minute, 5 seconds executing artifact transforms. We can also see in the top all the transform requests that it made, and you can go in and see all the time it took. So yeah, how did this task display itself before transforms were captured in build scans? We can do a little experiment. If you want to repeat it, this is how you can do it. You can disable the capture of artifact transforms in your build scan using this internal API. You can delete the transform cache and then rerun that build, and you can see that this task looks very different. You can see that the fingerprinting input time is now far longer. In fact, it's almost as if you added the executing artifact transform time to the previous fingerprinting input time, and that actually is the case. So basically what happened is before artifact transforms were in build scans, the attribution of the execution of the transforms would be attributed to the fingerprinting of that task's inputs. I know that's a very long sentence, but basically that means that this time, which wasn't there, was just counted in the fingerprinting inputs time. So yeah, just keep that in mind if you're looking at old build scans, or if you previously were wondering in a build scan, why is my fingerprinting time so long? It actually could have just been that artifact transforms are being executed. All right. I also wanted to point out that the Develocity API has transforms in it as of Develocity 2024.1. And so what that means is you can dive through all the information in your transforms in a programmatic way instead of having to examine each build scan individually. This is what the API endpoint looks like. And there's the docs at the bottom, but yeah, you can just find it on our website in the manual. These are all the things you get back, including whether it failed, it was successful, or the transform was from cache or up to date. And I think that's basically it for the webinar. I think we're doing perfectly on time. We just wrapped up 30 minutes. Hopefully we didn't lose everybody. I see there's a lot of attendees still there, which is great. I'm going to hand it back to Oliver, for, I guess, Q&A.
All right. Well, Nelson and Inaki, thank you both very much for your insights and time today. And thanks to our audience for tuning in. One question that is actually my own, I think I know the answer, but I want to confirm with you both. All of the screenshots, the drill downs and investigatory data that you've been showing us, is this all available in a free build scan that folks can go to today? Or is this sharing some more Develocity license-based goodness?
Yeah, that's a good question. Everything is available in the free build scans except the Develocity API. That's only in the paid version because you only get one build scan, so there wouldn't be a point of the API anyways. Great.
Yeah. That's what I was thinking. All right. Well, the place to go for that, folks, is scans.gradle.com, and we think you'll like it. So now let's turn it over to the Q&A. The first question we had is from a very active person in our webinar today, Tom. He asks, an artifact transform seems quite different from a Gradle task. How does Gradle determine when to execute transforms, and which tasks depend on the transform outputs?
Yes, that's a good question. So Gradle, as part of the execution engine, will automatically schedule transforms with the shortest possible chain in order to get you that dependency that you requested with the attributes that you requested. So if I don't know. As an example, there's like maybe two paths to get you a Dext jar, right? One is by taking class file and transforming it via the Dext transform, or another path could be, right? I'm not saying, this is the right way, but you could convert it to an AAR, then unconvert it from an AAR, and then Dex it, right? That's like another thing, but the execution engine will pick the shortest possible path for executing transforms. Yeah, that's basically how they're scheduled. Does that answer your question? If not, feel free to clarify in Slack.
Well, we've got another one from Tom. Is it correct to assume that a specific version of an AAR will be transformed once and retained indefinitely unless the Gradle version changes? Or are there other factors that can invalidate the cache for the specified AAR?
Do you want to take this one, Inaki?
Yeah, sure. So we don't have to forget that at the end, the inputs and outputs in terms of dependency transforms are dependencies, right? So there's like no task outputs, right? Or task invalidation in this case, right? Even though that we can use caching and up-to-dateness. So this is a slightly different behavior from the task. So if you have your transform that has been executed the first time and to a given dependency, and there are no chains on those dependencies, the transform is going to be up-to-date or from cache most of the times. Now, if you remove your Gradle user home or you remove the transform, the cache transform output, you're going to hit the local cache. But we don't have the possibility to rerun the transforms as we are doing with rerun tasks. So.
Yeah, and it's also subject to the Gradle home cleanup. So if you haven't used the transform in a period of whatever your cleanup period is, then it'll be removed.
All right, great. Thanks for that answer, guys. There's a couple questions about the material icons library transform case. A little bit more clarity about what was going on there. What was the dependency that was causing the long transform time? And one person mentions, they don't want to have to manually extract the required classes and copy them to the project source sets. So does that influence the project in any way negatively?
Yeah, no, that makes totally sense. So in this investigation, we are talking about now in Android. It's a small project, right? So we can afford to do this change, right? Providing the dependencies. But what is true is that this dependency has 11,000 classes, right? And it's affecting the transforms. So one option could be on a ticket with Google as well, trying to say that, well, this dependency actually is causing like this overhead on the bills, right? And let's see if they can provide a different solution. But so in our opinion, or in this case, I'm going to take it in my opinion, I consider that the size of the dependency of the library is too much and it needs to be reduced, right? So,
and I think the other part to the question, can you just repeat the name of the dependency, Inaki?
Material icons. Yeah. It's
Material icons extended, right? Or it's just material icons?
Let's see. Material icons extended Android. That's cool. Yeah.
All right.
Was there a second part to the question, or did we answer all of it?
I guess the question is, if someone doesn't manually extract these required classes, is there a penalty suffered?
That's a great question, and you can look at a build scan and see what the penalty is.
Yeah, there you go. Actually, so the question is maybe, but you can find out. Or the answer is maybe, but you can find out. Right. All right. There's a question. What happens during fingerprinting inputs? In quotes.
I can take that one. Gradle is basically creating a hash of, in a very simplified way, it's creating a hash of what of all the inputs to that task or that artifact transform. That's basically a summary of what fingerprinting input is.
Okay.
Yeah.
Well,
I mean, excluding the case where artifact transforms aren't captured. In that case, it's also executing artifact transforms. But normally it's just creating a simple hash of inputs. Mm-hmm. I assume that's what it was about, the question.
Well, I hope that answered your question. If you want to add a little more context to it, we'll be happy to get to that. Just a couple more before we end for today. And folks, if we don't get to your question, you can feel free to email me directly at owhite@gradle.com. And I'll be able to hopefully find the right person to answer that for you. There's a question, I like this question actually. Are there other things that library authors should consider for keeping transform time low in consumer builds? So for example, if you're the maintainer of now an Android, what might that person do to, let's say, get a head start on reducing cycle time?
I think to clarify, he means if you're the maintainer of the Android Gradle plugin, which is used.
Yeah, the author of the library, perhaps. I'm not sure if that's if we all understand the term in the same way.
Yeah. I would say that generally here applies the same software engineering approach, right? By keeping small pieces of compilation units when you are designing an API, for instance, when you are building your model, right? So you want to be concrete and offer only what is required in your API, for instance, or in your contract that you are defining in your library. So my answer would be like, apply the same common sense that you're applying in terms of modularization, testing, and everything there. Make it small.
All right. Let's see. Our last question that we've got time for today, regarding the caching aspect, is the cached output disregarded if the transform implementation class path changes?
Yes, that's correct. Sorry if we didn't mention that. Yes.
Okay. So a good old yes or no answer. That's always refreshing. I'm sure people are used to hearing, well, it depends, and we'd really need to see under the hood. Well, gentlemen, thank you very much. I think our audience today was very interested in seeing what you had to share. I hope we were able to answer enough questions. Like I said, you can email me. My email is in the chat window. If we didn't get a chance to answer some of your questions, there's a couple questions in there that are maybe a little bit too specific for us to answer in a Q&A for a webinar, but that doesn't mean we won't be able to answer it for you later on. So Inaki and Nelson, thank you so much for joining us today. The recording and slides will be provided to everyone who registered for this event sometime next week, so stay tuned for that. And with that, I will say goodbye.